Hello everyone, welcome to the final installment of this spring's series of Dave Does Pre-Calculus from Home videos. There's probably going to be more in the summertime, but for now,
Japanese
this is...
kitties. Hey,
There's some cat fighting happening.
what's wrong with you guys?
This is going to be the last one for the spring semester. The section that we're working on right now is section 7.5. We're doing complex numbers in polar form. This is part one. So first let's talk about the complex plane. I'm going to start by drawing some coordinate axes. They look like this. You are extremely familiar with coordinate axes. You've seen these things literally constantly for a long time. We are really used to looking at this in terms of an x-axis and a y-axis, and then we get coordinates that look like 3, 4 or whatever, and we put 3 on the x and 4 on the y, and we say that this is the point 3, 4. Yep, this is this is the noisy one. He's mad about it. Ashes, what's your problem? Why so noisy? Say hi to pre-calculus class, Ashes. He doesn't even know what's happening. He's just a miniature giant space puma. Thank you for our guest appearance. So, typically we have a point 3, 4. This is an x value, this is a y value. We put 3 on the x-axis, 4 on the y-axis, we get our point 3, 4. And that's pretty typical. What I would like to change about this is, in practice, very little, but in terms of paradigm, maybe a big change. Let's see. Instead of calling this the x-axis, I'm going to call this the real axis, also known as the real number line. I'm sure you remember number lines from something. Positive goes to the right, negative goes to the left. You have a number line. I'm going to call this vertical thing the imaginary axis. So, if I have a real axis and an imaginary axis, I can talk about this instead of as a point in a pair of xy coordinates. I can talk about this as a complex number, 3 plus 4i. And it works almost exactly the same. We've taken away the parentheses and the comma, and instead we have a plus sign and an I attached to one of these numbers, but functionally we're doing the exact same thing. We're looking at 3 on one axis and 4 on the other axis to give us this point. This is where 3 plus 4i sits on the complex plane. And we can do other numbers as well, like we could do -2 plus, or let's do big ones. Let's do -5 plus 2i is back here. Same as -5 comma 2 would be. -1 is right here, except that's -1 minus 1i. And 3 comma -2 is right here, except instead of calling it 3 -2, I'm going to call it 3 minus 2i. So, complex numbers functionally work exactly like xy coordinate pairs, except we just write them a little differently. And then this is called the complex plane. So, that's where we're going to start. We'll look at some complex numbers, we'll figure out what quadrants they're in, because the quadrants are functionally the same thing. We'll plot some complex points. It's all pretty straightforward. Here's where things are going to get weird. We're going to combine this idea of complex numbers on a coordinate plane with the idea from 7.3 of expressing rectangular coordinates in a polar form. So I'm going to go back to this one right here. This is the point, the 3 plus 4i. This is the point that I really want to work with right now. And the question is, if this were a regular rectangular point, it would be 3 comma 4. That's fairly standard. The question is, what happens if I want to express this in polar form? Well, first of all, I'll need the distance. And second of all, I'll need the angle. It's kind of like an r and a theta. That hasn't really changed since section 7.3. We're still looking for your r and your theta. And we can find those things. These markers are nearly done for. They're smudgy and a little gross now. So r squared is going to be the from 7.3 we had this, r squared equals x squared plus y squared. But in this case we don't really have x's and y's anymore, because this isn't a set of coordinates. This is a plus bi. So we're not going to do it like this. We're going to say r equals the square root of a squared plus b squared. This is the complex numbers version of the same Pythagorean theorem that you're well familiar with. And for this section, we're pretty much always going to use positive r values. So in the last section we had this ongoing challenge where I wanted to leave it in this form without any square roots, because sometimes r was positive, sometimes r was negative. So I didn't like this version with a square root in it. In this section, we figure that's been handled already. We've done our time with our negative radiuses, and now we can move on to a more sensible practice where we just say that the radius is always positive. This distance is always going to be positive in section 7.5. So r equals the square root of a squared plus b squared. For us, that means that r equals the square root of 9 plus 16, which is the square root of 25, so that should give me 5. R equals 5. So I know this distance. That's 5. There's that handled. Now I need the theta. And I don't actually remember the theta. Ugh. Okay, got it. Had to go visit my calculator for a second. So, we have our r, we need our theta. As usual, we have the tangent of theta equals, or in 7.3 we had this, the tangent of theta equals y over x. Here, we're going to say that the tangent of theta equals b over a, because again, we're not using x's and y's anymore. We're using a and b, the two components of a complex number. So for us, we're going to have the tangent of theta equals 4 over 3. And I just ran my computer to use a calculator. Turns out that in this case, theta is going to be about 53 degrees. For these approximations, it's generally easier to use degrees than radians, because in radians this is like 0.9, and without a pi attached to it, it's sort of very hard to conceptualize where that is. Like all of our standard radian measures have a pi in them, so when you're getting decimal approximations that don't have pi, it's challenging to know where that is. But in degrees we can say it's about 53, and that's all set. So I have a radius, I have a theta. I'm going to put this together in a second. First I want to answer the question that I'm sure many of you are thinking. If you just had to use a calculator to get the arctangent, what are we going to do on a quiz? Except in your mind it was probably phrased like, do we get to use calculators on the quiz? Because that's always what people ask me every time they think I use a calculator for something. The answer is still no. No calculators on quizzes. Still. Ever. If I put this problem on the quiz, then you can very safely tell me that theta equals the arctangent of 4/3 and leave it like that. That's fine. For your homework, there's going to be some problems where it wants you to estimate a theta value in degrees. Use your calculator for the homework. That's fine. On the quizzes, if I give you something like this, write theta as an arctan. If I give you reasonable numbers that show up on a unit circle, then you can use your unit circle to find out what theta should be, like 45 degrees or 30 or 90. If it's a nice angle that you're familiar with, you can just use the theta. So that's the calculator question answered yet again. Let's talk about r's and thetas and how we're going to put this together. In polar form, this point 3 plus 4i would be written as the real part. Remember, x equals r cosine theta, and except instead of using x's, we have a as our real part, and y equals r sine theta, except instead of using y's, we use b's as our imaginary part. So the way that we're going to write this in polar form is, instead of a 3, I'm going to write the 3 as 5 times the cosine of 53 degrees. And instead of b, I'm going to write 5 times the sine of 53 degrees times I. This is me transforming 3 plus 4i into 3. This is 3, it's just written a little goofy. This is 4i, it's just written a little goofy. And then to get this into standard form, I'm going to simplify it one step by factoring out the 5. So we'll say it's 5 times cosine 53 degrees. This is usually a hard bracket. 5 times the cosine of 53 degrees plus I times the sine of 53 degrees. So this, I should not have put a box around this thing. This isn't finished. This is the finished version. This is the polar form of 3 plus 4i. And it looks like a mess, but it's really just foregrounding two numbers. And it's the two numbers you would expect it to foreground. The radius is 5, theta is 53. It looks like a mess because it's long, because you have to write the cosine and the sine in there. But it's really just these two numbers, 5 and 53. And in a lot of engineering or sciences, I think this gets written as like 5 angle 53. So there are ways to shorten this in vocations. it gets shortened a lot. For math class, we're going to write it like this. 5 times the quantity cosine 53 plus I sine 53. Which, again, is not as long as it seems. There's just a lot of letters because you have to write a sine and a cosine. So, this is a complex number in polar form. And generally, I'm gonna erase some stuff so I have room. Generally, when you have a number like, not like that. Generally, a number like a plus bi, this is sort of like the rectangular form of a complex number, can be written in polar form. Let me write that, rectangular. Can be written as r times cosine theta plus I sine theta. This is the polar form. And this is a lot of what we're going to be doing in this section, which is honestly almost exactly the same as section 7.3. Like, very little has changed. This is a complex number instead of a pair of xy coordinates, but that's essentially the only difference. The way that we write them is all that's different. Like, all of the math is exactly the same. We're still going to be using the Pythagorean theorem to get r's, and we're still going to be using arctangents to get thetas. Or if we're going backwards, if we have a polar form and we want it in rectangular form, we're still going to be taking the sine and cosine of your angle and multiplying them both by r, exactly like we did in 7.3. X equals r cosine theta, y equals r sine theta. We're just calling them a and b now. So, to be very honest, almost nothing has changed, just the way it looks. So, more of a paradigm shift than a explosion of new material. There is more that we have to talk about though. I'm going to cut the video here and I'll start part 2 with another example, and then we'll get into the exciting stuff.